Yeah, so that's why
Hit record.
Okay, so good morning. Our first speaker today is me. And I will talk about the primitive element theorem for fields of different operators. First of all, on behalf of the organizers, I would like to thank you all for coming and making this event so intense. So we're in the end of this intense event. So today, Saturday morning, I'll try to give Saturday morning talk. Okay, so if it's too not Saturday morning, just tell me. Okay, so primitive element theorem. Throughout the talk, all fields are of characteristic 0. No positive characteristic in the next hour. So what's the classical case? If I have no operators, I have just usual fields of characteristic 0. Then the theorem says the finitely generated extension of fields and algebraic then there exists a single element that generates the larger field over the smaller field. Okay, and we call this element primitive element. So this is a classical statement. It's sometimes referred to as Artin's primitive element theorem, but it seems that it has been known for years before. And well, why is this statement useful? So it's an important. First of all, it's an important theoretical tool because it sort of brings separate algebraic numbers to common denominator, so to speak. And from this perspective, it's also used extensively in computation, because all the computation that are done with algebraic numbers are done by bringing them all to the common field, because then you have some common grounds, some normal forms, and it's also used to represent algebraic varieties. There is so-called geometric resolution construction that represents now algebraic varieties in terms of primitive element of certain associated extensions. So there are different uses of this, and this is an old result. I would like to change the setup a bit to get new results. So before I will talk about any results, I will consider two simple examples that will motivate what will go on throughout the talk. Sorry. Sister examples. My first example will be an extension of field of complex numbers by two functions, by function x and by function e to the x. Okay, so my f is c, my e is this bigger field, and we know that x and e to the x are not algebraically independent, so to understand this degree of E over F is equal to 2. Right? So that standard field theory says us that in this case we have no chance to generate E over F by a single element if we use only field operations. But now what we can notice is that both these fields are closed under differentiation, under d over dx, right? So if we enrich our language with this operation, so we will use arithmetic operations and derivatives, then we can do more. So in this case, we can consider, for example, alpha to be the sum of these two functions, and then it turns out that you can express both of these functions in terms of alpha. So because if you want to express e to the x, well, what you can do, you can just differentiate this twice, right? So x will disappear, e to the x will remain unchanged. So this is just alpha double prime. And then x can be expressed like this, right? So I subtract e to the x from here. Okay, so I add the operation, my power increases, I can express more. And let's now consider a different field extension, also functions. I will add x and the gamma function. Okay, so this will be my f and e in this case. And again, we know that, yeah?
So for that expression, is there an order bound? So an order bound for the differential equations that those.
Well, I didn't do any like general setup, but if you talk only about derivative, yes, you don't need derivatives of order higher than transcendent degree, higher than transcendent degree plus 1, just to be sure. Yes. So it will not be infinitely large. For ordinary case, for partial, it's a bit different. Okay, yeah. So this is also field extension, and these two functions are also algebraically independent, right? So the transcendent degree of this extension is again 2. So from the point of view of like, classical field theory, we're again in trouble. And again, we just can note that we have one more operation we didn't use yet. So both these fields are closed under shift of the argument. So if I introduce sigma that sends x to x plus 1, then through the functional equation for gamma function, shift of gamma function is still in this field, right? Because it's expressed in gamma function and x. So what I can do now I can actually get a primitive element even easier. I can set up such that just alpha is the gamma function itself. Then I have gamma function expressed in terms of alpha already. And if I want to express x, I just shift the gamma function. Oh, it's sigma, thank you. Oh, it should be alpha, yeah. Sigma. Okay, so we observe that some extra operations, derivatives or automorphism, make us more powerful in terms of what we can express with a single element. So let us try to derive some general statements about this. Before we'll derive any statements, let me review what statements have been derived. Because this is an old question and there are very old results. So for our results. So first I would like to talk about the case of PDEs. So for results, start with PDEs. More precisely, I consider fields with commuting derivations. Derivations. Okay, and I will refer to such fields as delta fields. Okay. Then there is a theorem by Kolchin. It's actually not that far from the original Artemis result. It's like 10 years after or something. So that if I have, I will state and I'll explain some things that are in the statement. So let us again have an expression I'll have very similar statement to the classical, just I will insert some deltas. So this extension should be finitely delta generated. And delta algebraic. Then I impose one extra condition that will be very important for us in what follows. So if I consider restrictions of the derivations on the base field f, so let these restrictions be f linearly independent okay, so this basically means that field f is non-constant enough.
What?
Non-constant enough.
It's very non-constant.
Very non-constant, yes, yes, yes. So some of you might be familiar with another way to formulate this in terms of Jacobian metrics. This is the same. This is going to prove that this is equivalent. So then, there exists an element alpha such that E is delta generated by F and alpha. And let me say a couple of words about terms delta generated and delta algebraic. So when I say delta generated, I mean generated using field operations and derivatives. Okay, so this means that there are some finitely many elements of E, so that E is generated by these elements and all their partial derivatives. Okay, and when I say delta algebraic, this means that every element satisfies some nonlinear partial differential equation.
Non-trivial.
Well, non-trivial, maybe nonlinear.
It can be linear.
It can be linear, but can be nonlinear. Yes, non-trivial and maybe nonlinear. Okay.
What you said was non-linear.
Yes, yes, I said nonlinear. I meant non-trivial and maybe nonlinear. Okay, just to prevent misunderstanding. But I paused it. That happens. Okay. And this is an old theorem, and it has been used a lot. So it's also a fundamental theoretical tool in differential algebra. Use it, for example, when you prove embedding theorem that differential fields actually live in meromorphic functions used in Gleb theory. And however, I would like to make remarks. So before I make remarks, I would like to specialize this result. So let us see what does this result say for the case when I have just single derivation. Okay, so special case, it's corollary basically. Then m is equal to 1. Okay, then I have finally delta generated delta algebraic extension. And now the statement that these restrictions are linearly independent, right? So I have now just one derivation. So this linear independence recasts into the statement that let delta be non-zero on F. Okay, so the ground field is not the constant field. And then, indeed, again, there exists alpha D such that E is generated, delta generated by F and alpha. Okay, so the reason I wanted to state this special case separately is the following, because I would like to make 2 remarks.
Doesn't apply to the example, right?
Exactly, this is my first remark. So my first remark is it doesn't apply to the last example I had there, right? So it doesn't apply to the extension that extends C with functions x and e to the x, right? Because C is a constant field, right? So it doesn't work here. And in general, if I extend C with certain functions, I cannot apply this theorem. And another context there I would like to be able to apply this theorem, but still cannot, is the context that Remy was talking about yesterday, is that if you have just x is k variety plus a vector field, what it recasts to is that field of rational functions of this variety.
What is K?
K is, oh, sorry, K is just some field of characteristic 0. Oh, let's for simplicity put it C. So I take rational functions from this variety, and then vector field induces a derivation there. So this is extension of C plus derivation. And again, since vector field acts as 0 on constants, I still cannot use this nice theorems to work with this case. Okay? So it would be great to have something that would be applicable here. And for special case m equals 1, there is. And this was one of the results of my PhD thesis. So I actually will not. So my theorem contains just one line. So this is whole theorem. Okay. So you don't need f to be non-constant. You want just the big field to be non-constant. And this is a much more natural condition, right? Because if your bigger field is constant field, then you don't have differential field basically, right? Because zero derivation is nothing. It doesn't give you any expressive power. Okay, so this is sort of the end of the story if you have just single derivation.
It's false enough. The theorem is false enough.
Yeah.
Which theorem?
You don't get a primitive extension.
Well, I mean,
Like-
if it's 0 on E,
It's 0. Like
well,
in case
unless it's generated by one element, right? So of course there are still some general examples, right? When they're like, but of course, yes, if you don't have any non-zero derivative, then you don't hope for anything better than the classical theorem. Okay, so this is what we have, but it's still it's only for m equals 1, right? So it doesn't generalize the bigger causal theorem. Okay.
Could you repeat the theorem?
Which one? This?
Yeah.
Yeah, so all the same. So you have extension of differential fields, and it's finitely derived and algebraic. And delta is non-zero on E.
Then?
Then there exists green defendant.
Oh, then.
But even when it is down to 0 on E, then you just fall back to the classical.
Yes.
So you can remove the hypothesis.
Well, no, but
It's no longer.
no, but you see, if you have a purely constant field, it's very differential algebraic, right? It also implies x prime is equal to 0. So somehow, in this case, derivative like hurts but doesn't help. Okay, so this is what is known about differential case. What about shift? What about shift? So this is now we consider fields. With an automorphism sigma. Okay, and I will refer to them as sigma fields. Then what we do now is a theorem by Kohn 1965. So what it says is that, okay, again, let this be finitely sigma generated and sigma algebraic extension. And again, we have condition on the ground field. Okay, so and also let the order of sigma on F be infinity. Okay? So there is no finite power of sigma that is identity on F. Then there exists alpha such that it is sigma generated by alpha. Okay, so the structure of statement is exactly the same. So I have finite generation, I have algebraicity, I have some non-degeneracy condition, and then I get the result, yeah?
Is there a version for several commuting?
I'm not aware of any. Well, I mean, I will present one, but before that I'm not aware of any. And again, this is an important theorem. Again, a fundamental tool when you study different fields. But I have again two remarks. So first remark that it doesn't apply to the example, right? So it doesn't apply. This example. And again, so there is an interesting case when you study with a variety. So if X is against C variety plus an automorphism, of this variety, then again it recasts into field of functions plus automorphism that acts on the ground field as identity. In both these cases, this theorem is not applicable, and at least for the first one, we do know that it's such that it is true. Okay? Right, yeah?
Cohn's theorem is just a characteristic zero?
No, for characteristic P, there is a version, but it has some extra conditions. It has also, he formulates theorem not just for automorphism, but for endomorphism, but this is effectively the same, because for endomorphisms, what he says is that you can generate a subfield such that you can put the bigger field into the subfield by endomorphism. So it's the same as going to inversive closure and working with automorphism. But for quasi-characteristic, there is a separate statement, but there is some extra assumptions. I mean, also in classical case, right? You can do something quasi-characteristic with assumption of separability. So that's a situation. Okay, so far so good. Great. So now, what do we want to do? So I have two goals. First goal is remove assumptions on the ground field. Okay, like what had been done for the case of one direction. And the reason I would like to do that is that if I do that, then I will have a theorem that's applicable to examples of the form I take just complex numbers and adjoin some functions. And this is what happens often, right? You start complex numbers and you solve some equations and adjoin their solutions. And also it will be applicable, if I do it in a nice way, to the examples coming from algebraic geometry. Examples from varieties. Like a variety with derivative with vector field or a variety with an automorphism. And my second goal is to allow several automorphisms and mixed cases. Okay, because, yeah?
Why do you assert that your variety comes with an automorphism rather than the more natural, more general setting with a correspondence?
Well, first of all, I would like to keep things simple, and second, I think correspondence might give you not automorphism but endomorphism here, right? So I wanted to translate to automorphism on the field of functions.
I see, okay.
Yeah, because otherwise I'll have to take inverse closure. Okay, so the setup for this, for the main theorem of the talk, will be the following. I have derivatives, set of derivatives delta, like in the Colchin's theorem, and I also have automorphisms. Sigma r. And what I require that they all commute with each other. Okay, and in this setup I will use terms delta sigma field. Okay, this is a field generated by this is a field equipped with derivations and automorphisms from this set. And I will use also terms delta sigma generated. Okay, again, in the sense that it's generated by using field operations and derivations and automorphisms. Okay, and I will use term delta sigma algebraic. Okay, meaning that element is delta sigma algebraic if it satisfies certain non-trivial algebraic relations that involves field operations and these operators. Okay, so just direct generalization of what I had before. And now the statement is that let me have an extension that is finitely delta sigma generated and delta sigma algebraic. Okay, so far no surprises, just virtualization. And now the important question is what sort of conditions I impose regarding non-triviality of these operators. So I'll assume two things. So one thing will be very similar to what Colchin did, just with bigger fields. So I take these derivatives on E, and I require them to be linearly independent over E. Okay. So again, I replace F in Cauchy's theorem. So in Cauchy's theorem, you take restrictions of the derivations on F and require them to be linearly independent there. I'm fine with linear independence only on the bigger field. Okay, so the field F might be absolutely constant field, whatever. And second thing, so how constant condition comes here? What I will say, and then I clarify it a little bit. So I take this sigmas, right, and they form an abelian group, right? So I can multiply them by composition, and what I ask is that they Z linearly independent. Meaning that
Solution derivatives commute with each other.
yes,
With each other.
everybody commutes with everybody.
And what?
Everybody commutes with everybody.
Very nice.
Yes, very peaceful situation. Okay, so they are Z linearly independent. What I mean by that is that if you have a set of integers not all zero, then the corresponding monomial is not identity. It's not identity on E, on the bigger field. Okay, so and if you look at the Con's theorem, this is indeed an extension, right? Because if I have a single automorphism, then its Z linear dependence would be exactly it having a finite order.
You think not there are cable.
No, if they are not all zero, then this is not identity. No, I have negation in second idea. Okay, and then then there is primitive element. Then there exists alpha and E such that E is delta sigma rated by F and that.
And so with this theorem, is this also the end of the story?
I'll say a couple of words about this. So yeah, so let's now figure out how what this theorem brings into the picture. So, yeah. If I take sigma to be an empty set, so no automorphism, right? So what I get is Cauchy's theorem, but with linear independence, not for the ground field, but for the bigger field. Okay, so it's, in this case, it's strengthened Cauchy's theorem. If I have no automorphisms and I have just single derivation, this is exactly my old results. My old results is 2015. And finally, if I have no derivatives and just yeah, this equal and this equal. Thank you. And this is just one automorphism, that I get strengthened Con theorem. Okay, because this linear independence in the case of one automorphism is exactly having an infinite order, but on the bigger field, on E, and it doesn't require anything from ground field. Yeah, so in particular now, this theorem is applicable to all examples I have considered so far. Now, regarding how strong are these conditions? So let me just show you what happens if you violate this linear independence, roughly, on a more or less specific example. Okay, so assume that I don't have any automorphisms, and I have just two derivations. And, well, let's assume that they are, by some reason, linearly dependent. For simplicity, I will take some very simple dependence, like this. Then what I can do, I can consider extension of delta 1 fields, and then I'll make it just only finitely generated, right? So finitely generated, but maybe of high delta 1 transcendence degree. Okay, so it will be delta 1 finitely generated, but of high delta 1 transcendence degree, meaning that it is generated by finitely many elements using delta 1, but cannot be generated by a single element. And now, if I want to have this condition fulfilled, then delta 2 can be defined here uniquely, right? So I can now define delta 2 in negative 1/2 of delta 1. Okay, and what happens if I do introduce now delta 2? So first of all, in terms of what can I generate, I gain nothing, right? Because this is just the same. Okay, I do not generate anything new. But all of a sudden, my extension becomes delta algebraic, right? Because now every element in E satisfies delta 1a plus 2 delta 2a is equal to 0. Okay? So I couldn't generate by a single element. I added nothing to my expressive power, but I have delta algebraic extension. Okay, so I cannot generate it by a single element still. And this is sort of not a special example, this is sort of a prototypical example, right? Because if you have a linear dependence between derivatives, this means that one of them brings almost nothing to the table. But everybody is algebraic, is delta algebraic. Okay? So basically, if you have this dependence, you come into theory of delta, just finitely generated delta fields. Yeah?
So this theorem in particular says that there is no way to somehow do this sort of thing involving both the delta and the sigma.
Yes, that's very surprising for me also. So this condition, it is for deltas and sigmas separately. So they sort of live in parallel worlds. They don't interact in this sense, if they commute. That's very surprising for me also, but well, it's true. Okay, so and what you can cook up similar example for Z linear dependence, right? So again, if you have Z linear dependence between automorphisms, that one of them is like almost generated by another. other one. Okay, so there is still some small gap for improvement because, well, if you have, for example, an automorphism of finite order, this is still something you can do with it, right? It's still not a usual field. So there might be still some extra theorems that will say that, well, if automorphism is finite order, but it is good, then you can still do something. And in fact, I have such statement. If it's like the order is high enough, you can do something still. But apart from these special cases, this is more or less the end of the story again. So I'll spend a couple of minutes. I will not talk about how I prove this theorem, unfortunately, or maybe luckily. But I will prove how I will talk how I will not prove this theorem. Okay? So what not to do. Okay, so if you look at proofs of classical primitive element theorem in algebra textbooks or on Cohn's or Colchin proofs, they follow a similar strategy. So, strategy of classical case is Colchin and Cohn. So the strategy is the following. So first of all, this is not a big step, but just a natural thing to do is to say that let's restrict ourselves to two generated expansions. To the case that E is generated in a suitable sense by F and two elements, A and B. Okay, so and by generated I mean like delta generated or sigma generated, depending on the context. And then what all these proofs do, they look for primitive element as A plus lambda B, where lambda is generic enough element of F. Okay, this is what happens in all these three books. Of course, there are many details to feel. I don't say that these proofs are like the same. Of course, there are all subtleties with all the cases, but this is a general framework. So why I don't want to do this is because this doesn't work, and this doesn't work not in the sense that I can do it, but this is just not true that you can always find a primitive element as such linear combination. And I will show you just a short example that illustrates this. So, example, I will consider just one derivative and no automorphisms. So I'll look at the extension that I add x, log of x, and log of 1 minus x. Okay, so what one can see is that these two, they can be taken as delta generators. Right, because the derivative of log is 1 over x, so you can get 1 over x from it. So they can be taken as A and B in this approach. Okay, so this can be taken as A, this can be taken as B. Okay, and let's try to find the primitive element as their linear combination. Okay, so consider alpha, that is log x plus lambda log 1 minus x, where lambda is a complex number. And that what you can observe is that the derivative of alpha is the rational function, always, right? So what will happen is that if you consider a field generated by alpha and its derivatives, then this part will be in rational functions. So the whole field will have transcendence degree at most 2. But these three functions, they are algebraically independent. So you can do that. And you can cook up a similar example for shift case, but instead of logs, you take some specialized Hurwitz-Zeta functions. So it also can be done with some classical stuff that exhibit the same behavior. So, and what happens, let's just see, to work about it without writing anything. So, in the 2015 theorem for ordinary case, what has been done is that I considered A plus some polynomial of B. Of high enough degree, and that worked in 2 stages. Okay, we have 2 stages of such procedure. What I do now, let me just say something very strange first. I consider A plus just some function of B. Well, what is function, right? We cannot take any functions in absolute fields. Okay? Well, I will say that analytic function would be good enough for me. So I consider Taylor series. Right? But this also doesn't quite make sense still, right? Because I cannot consider infinite power series in absolute fields. So now what I do, I truncate it, right? I truncate it at high enough order so that it's now an algebraic object. And I work with this.
So how is this different from the previous case?
Bingo! Yes, it's exactly the same. Up to a minor thing, this one. It turns out that if you have these factorials, they somehow allow you to do sort of lizard-style things. Okay, so I have cut the tail of this series, but then in the proof, I go to Keller differential, and I grew the tail back. Really, so these factorials, they just explain you how to grow the tail back. And once you have the tail back, you are in functions, you are very good. And for the rest in the paper, just somehow, in the paper, I have a separate proof for ordinary differential case is just 2 pages, so it's as long as Colchin's proof, and much shorter than my old proof. Just 2 pages for differential case of this stuff. But general cases is, of course, longer. And before I stop, I would like to acknowledge the funding that supported this research. It was NSF and the University of New York. Thank you very much for your attention.
So is the proof constructed then?
Yes, you know this M. Yeah, well, so you know this M, but in the case of several operators, this M is expressed in terms of Colchin polynomial. Somehow. And moreover, in the case of several operators, you don't have univariate Taylor series, you have multivariate Taylor series. But still, this can be done. And basically what I prove is if N is big enough, and I say what is big enough, then generic lambdas will work.
You get a bound.
Yes, I get the bound for N. And it's explicit once you have Colchin polynomial. And that's also constructed.
How do you distinguish A and B?
Yeah, that's what. So do first linear change of variables so that B is non-constant enough, right? So I know that my larger field is pretty non-constant, so I organize B to be non-constant enough. Yes, so they are not symmetric in this sense. Yeah? Yeah?
Is the, so the statement false when we have two non-commuting automorphisms, no derivation?
I don't know. I just don't know. But I think if you have to non-commuting. No, I don't know. Yeah, I understand what you're asking about. No, I don't know. I don't know. Might be true. Yep.
So maybe just a comment that I was asking about does fit into the formulas of your theorem.
Oh, really?
Yeah. So you're not acting on the function field of your variety anymore.
Okay.
You're acting on some algebraic extension of it.
Ah, and then this
And it's not-
finite one is hidden.
Yeah.
I see.
But the algebraic extension is not finite. It's potentially an infinite algebraic extension. But it's still finitely sigma generated.
Ah, oh, that's nice. That's nice. Thank you very much. I have to look at it more closely. I didn't think about this. Other questions?
All right, thank you.
Good stuff.